All right, we start chapter 8. Take my time with this because our test will be at 6, 7, and 8. So we're talking about acids and bases. The earliest definition was given by a man named Arrhenius. And he said an acid contains a hydrogen atom and dissolves in water to form a hydrogen ion, H+. So here we have hydrochloric acid in water gives us H+ and Cl-. According to him, a base contains hydroxide ion and dissolves in water to form OH-. So sodium hydroxide dissolved in water gives us Na+ and OH-. So that's pretty simple. If you see an H, you have an acid. If you see an OH, you have a base. That works for quite a few things. The names of common acids are derived from anions formed when they dissolve in water. So HCl, the anion is chloride. The acid is hydrochloric acid. Sulfate, the acid is sulfuric acid. Sulfite is sulfurous acid. Now his definition is good, like I said, for quite a few things, but sometimes inaccurate. H+ doesn't exist in water. What actually exists is called the hydronium ion, H3O+. So H plus H2O gives us what's called the hydronium ion, H3O+. That's what's actually present in water, H3O+. Different definition, more widely used, is the Bronsted-Lowry definition. A Bronsted-Lowry acid is a proton donor, donates H+. A Bronsted-Lowry base is a proton acceptor, takes H+. So here HCl plus H2O goes to H3O plus Cl-. So the HCl gives its H+ to the H2O. So it donates, so it's an acid. The H2O takes the H+, so the H2O is a base. So Bronsted-Lowry acid must contain a hydrogen atom. So here's some common ones: hydrochloric, hydrobromic, nitric. Sulfuric actually has 2. Acetic acid. Notice, even though there's 4 hydrogens in acetic acid, this is the only one that forms an acid, the one attached to the oxygen. The ones attached to carbon don't come off. So, acetic acid, pure acetic acid, 100% acetic acid, called glacial acetic acid, is A, flammable, and B, is so strong it'll burn the skin right off your body. But if we dilute it to 5%, you all eat it. It's vinegar. Citric acid is found in fruits, which is why they use the new cleaners that have the orange and they have citric acid in it, which is why oranges, lemons, and that they taste that sour taste that's from acid. Carbonic acid, H2CO3, that's what makes your Coke in that fizz. and also gives it a slight tart taste. So we said a Bronson-Lowry base is a proton acceptor. It has to take an H+. So a base must contain a lone pair of electrons that can be used to form a new bond to the proton. So here we have ammonia. Remember, ammonia from when we did Lewis diagrams has this lone pair of electrons. If we put it in water, it will accept an H+ from the water to give us NH4+ plus OH-. Remember, OH- we said was the definition of a base. Wait, if this is the base, then water must be an acid. But in the previous example, we said water was a base. So water, ammonia are bases. If we look at OH and metal salts like sodium hydroxide, potassium hydroxide, magnesium hydroxide, calcium hydroxide, those OHs are bases. Calcium carbonate is a base. That's what's found in Rolaids. Tongues, that sort of thing. Chalk, calcium carbonate's chalk. Ammonia is found in, obviously, cleaners, like Windex and that. Sodium hydroxide is found in Drano. Sodium hydroxide is lye. So if we look at an acid and a base, we have HA for the acid, a base with a lone electron pair. H+, just the H+, goes over here to give us HB+, and the A keeps its electrons and becomes A-. That's a proton transfer. So the HA becomes A-. So if this is the acid, we call the result the conjugate base. Here, this is the base. The HB+ is the conjugate acid. If you look at the reaction going back from right to left, to go back this way, the HB+ has to donate its proton to the A- to give you HA, so that makes this the acid. This accepts the proton, so this is the base. So the acid becomes the conjugate base, the base becomes the conjugate acid. Yes?
So what essentially is happening when you use an acidic cleaner to clean something? Is that related to chemicals or chemistry? Is it bonds rebuilding one against
When you're using a cleaner,
like a citric acid cleaner or vinegar or carbonic acid?
well, if you use citric acid or vinegar to clean something, usually what happens, for example, bathtub cream, which has nothing to do with people being dirty, but has to do with the fact you have hard water. Hard water deposits, and you get calcium salts that deposit on the rim. They don't dissolve in bleach cleaners, they dissolve in acid. So the sources of acid are citric acid. You can use vinegar to clean it. Ammonia-based cleaners won't dissolve it. So if you get that stuff, CLR, for lime and rust stains, That's an acid-based cleaner. So that dissolves that. So it actually displaces the, it goes into solution to calcium stuff that makes different salts that's water soluble, so they get flushed down.
They're great for washing.
Well, they're all ionic, they're salts, so they form different salts that are more water soluble. And then as they, so when you do it, I don't care what it shows you on TV, it's not like squirt, squirt, you just wipe it off. Squirt, squirt, let it sit there for a while, then wipe it off. It's got to have time to react. So if you look at HBr plus H2O, the HBr donates its proton to the H2O, so we get H3O plus and Br minus. So HBr donates the proton, it's the acid. H2O accepts it, it's the base. Br minus is the conjugate base, and the H3O plus is the conjugate acid. We call the HBr and Br minus conjugate acid-base pair. H2O and H3O are conjugate acid-base pairs. So this is one pair, this is the second pair. Notice the net charge on both sides is the same. On the left it's 0. On the right we have a minus and a plus, which is 0. So if I ask you to identify conjugate acid-base pairs, in this case, the pair would be HBr, Br minus, 1, and H2O, H3O plus is the other. So when a species gains a proton, it gains a +1 charge. If a species loses a proton, it effectively gains a -1 charge. So the H2O gained the proton, it becomes H3O plus. The HBr lost the proton, it becomes Br minus. There's compounds we call amphoteric. They contain both a hydrogen atom and a lone pair of electrons. It can be either an acid or a base. This is water. Water has a lone pair of electrons. It can accept a proton to become H3O plus. So that makes it a base. It can also donate a proton, which makes it an acid, and there's the conjugate base. So water, depending on what you're reacting it with, can be either an acid or a base. So it's amphoteric. So in the top equation, what is water? An acid or a base? Is it, in this equation, is it accepting a proton or donating a proton? Accepting. It went from H2O to H3O plus. So that means it's a base. Bottom one, what is it?
It's an acid.
It's an acid because it donated a proton to the NH3. So in the top equation, tell me the two conjugate acid-base pairs. HCl and what? HCl minus is one. What's the other pair? Yeah, there's only two left, H2O and H3O plus. In the bottom one, what are the conjugate acid-base pairs?
H2O and OH minus,
That's one, and the other one is
and H3 and
H4 plus, yes. On the right side of the top equation, which one is the conjugate acid? It's H3O plus.
H4.
Yes. Which one's the conjugate base? It's got to be Cl minus. The bottom one, which one's the conjugate base?
Do the H2O.
OH minus.
OH
Which one's the conjugate acid?
H3.
And H4 plus. If I'm talking about conjugates, I'm talking about the right side of the equation. This is going to donate a proton to this to give us water, so this is the conjugate acid, this is the conjugate base. This has to donate the proton to the Cl minus to give us HCl, so this is the acid, this is the conjugate base.
Acid donate to the base of C.
Yep. Acid and base strength. When a covalent acid dissolves in water, the proton transfer that forms H3O plus is called dissociation. Okay? When a strong acid dissolves in water, 100% of the acid dissociates into ions. So here we have hydrochloric acid, which is a strong acid. Now when we talk about strong and weak in chemistry, we don't mean the ability to do damage. Acetic acid is a weak acid, chemically. However, pure acetic acid, I told you, will take the skin right off of you. So here, HCl, H2O, this reaction goes completely to H3O plus and Cl minus. So common strong acids are HI, HBr, HCl, H2SO4, and HNO3, nitric acid, which is my favorite acid.
Why?
Why? Because when I was in graduate school, being a poor graduate student, you look late at night and you'd only have a couple pennies in your pocket, and you were made out of copper. Nitric acid dissolves copper. So if you took nitric acid, a beaker, put it in the fume hood, and add some copper pennies, and waited just the right amount of time, it would start dissolving the pennies evenly all around. If you stopped it at just the right time, it would be the size and weight of a dime. And it would work just like a dime in a vending machine.
Oh, you can turn 1 cent into 2 cents.
Yeah.
I'm glad I asked why.
Yeah, you got to do the fume hood because it gives off very toxic gas. And it's not exactly, what's the term, legal? But the statute of limitations is over. A weak acid, when it dissolves in water, only a small fraction of the acid dissociates into ions. So there we have a double arrow. Notice it, the arrow going back to the left is longer, which means it mostly stays undissociated. Only a very small part dissociates. This is acetic acid. So only a small part dissociates.
So the long arrow means that it's
More to the reactant side. So common weak acids are phosphoric acid, hydrofluoric acid, carbonic acid, which we said is in Coke, Pepsi, and all that stuff, and hydrogens, hydrocyanic acid. Again, don't confuse weakness with safety. Hydrofluoric acid dissolves glass. You have to keep it in a plastic bottle. In fact, that's what they use to etch glass. And if anybody ever was aficionado of Breaking Bad, the first season, the guy's assistant killed somebody and they wanted to dispose of the body by dissolving it in hydrofluoric acid. So the chemistry teacher said, make sure you put a shower curtain in the tub. This shower curtain's made out of plastic. The ceramic tub, ceramic is a form of glass. So it's not fiberglass, it's glass.
Fell to the roof.
So they put the body in there and they added a couple gallons of hydrofluoric acid that was doing its thing on the body, but at the same time it was eating the ceramic tub, and it ate through the bottom of the tub, and the tub went through and everything went through the floor and crashed down below, and there was body parts and all kinds of stuff that they had to clean up. Hazmat suits. So, once again, a lack of chemistry knowledge. You can actually get HF, well, a form of HF at Michael's craft store, specifically for etching glass. And it says on there, be very careful. Hydrocyanic acid is what they use in the gas chamber to kill people. Supposedly it smells like bitter almonds, but apparently if you smell bitter almonds, you're dead. So he said a strong acid completely dissociates in water, and a weak acid is mostly undissociated in water. A lot of your weak acids are organic acids, citric acid. So, if I handed you ascorbic acid, how many would eat it?
For what?
Ascorbic.
Eat it.
You can?
Hey, isn't it like in food?
Think so.
Ascorbic? Like fruits?
You know what it is?
Yeah, that's a fruit, so I've seen it. I'm a label reader on the grocery shopping.
When a strong base, similarly, when a strong base dissolves in water, 100% of the base dissociates into ions. So sodium hydroxide is a strong base, dissociates into ions completely. A weak base only partially dissociates. So ammonia only partially dissociates. So ammonia is a weak base, yes.
So would our vial, I guess we call it, be an acid since they tell us drink some hard foods or something, I guess to dissociate better?
The bile, you mean from our stomach? That's a strong acid. That's hydrochloric acid.
And that's why they say to drink something in the morning or something like that. So they can dissociate.
Well, you want to kind of dilute it a little bit. Otherwise, you get susceptible to heartburn. Because your stomach acid is strong enough to dissolve metal. Again, there was an episode of CIS where they captured the doctor that does all the autopsies and took him to some mountain cabin and had him locked there with a body, and the body supposedly dead. The guy had put something in his body, they wanted him to get out. So he's chained to the table. When the guys left, they cut the guy's stomach open and took the stomach acid, put it on the chain, and dissolved the chain. Probably not as fast in real life as it did on the show, and he escaped. Now our stomachs have mucus lining, which keeps it from this hydrochloric acid. So if you eat a lot of food, if you're sitting there, watching your favorite football team get beat up, eating a lot of chicken wings and that, you're producing a lot of stomach acid. Then you lay down, and stomach acid comes up out of your stomach into your esophagus. Your esophagus doesn't have that lining. You have heartburn. It really is burning. So or people that have problem with their stomach mucus, too much acid, they'll start burning your stomach. Those are called ulcers. So you can now, you take an antacid, which is a base. You can take Rolaids, Tums. You could just take, really, real quick, baking soda, 2 teaspoons of baking soda in a glass of water, and drink it. And that'll neutralize a lot of your acid. But it'll produce a lot of gas. You'll burp a lot. Yes?
So why is it like if you take like Advil or something on an empty stomach, they say you get like a stomach ulcer?
Advil, aspirin. Aspirin is acetyl salicylic acid. You're adding more acid on top of the acid. And sometimes those things, those drugs interfere with the hormones that produce the mucus. So you start reducing the mucus in your stomach. It's more susceptible to heartburn. Yeah, so a lot of times we'll say take drugs with food. So a strong base completely dissociates, a weak base mostly undissociated. So strong acid forms a weak conjugate base. A strong base forms a weak conjugate acid. Similarly, a weak acid forms a strong conjugate base, and a weak base forms a strong conjugate acid. So whatever's strong becomes weak, whatever's weak becomes strong. So here, water can actually react with itself. This can act as either an acid or a base. And we can get HCO plus and OH minus. This is called the autodissociation of water. So pure water has really low concentrations of both those ions. Turns out the concentration of each is 1.0 times 10 to the minus 7th molar at 25 degrees C. If we multiply this, because we have we haven't really talked about equilibrium, but this is called equilibrium constant, or the ion product. It forms two ions. If we multiply both of these together, and this is specifically for water, and it's W means it comes out to be 1.0 times 10 to the minus 14. That's the ion product constant of water. So that's a constant for all aqueous solutions at 25 degrees C. That's an important number to know.
So 1.0 times 10 to the minus.
Yep. And to know this equation, the Kw is equal to the H3O plus times the OH minus. So if I give you either the OH minus or the H3O plus, you can figure out what the other one is. If I know the H3O plus, the OH minus is equal to the Kw divided by the H3O plus. Or the OH minus concentration is equal to 1 times 10 to the minus 14th, because that's Kw divided by the H3O plus. If I give you the OH minus and ask you what the H3O plus is, the H3O plus is equal to Kw divided by the OH minus, or 1 times 10 to the minus 14th divided by the OH minus concentration. Brackets around it mean concentration. So if I say the OH minus concentration is equal to 1.0 times 10 to the minus 8, what is the H3O plus concentration? You tell me. And don't use your calculators. I know, it wasn't fair. I didn't let you use your calculators. Okay, if the H3O plus concentration in a cup of coffee is 1.0 times 10 to the minus 5 molar, then the OH minus can be calculated as follows. 1 times 10 to the minus 14 divided by 1 times 10 to the minus 5 is 1 times 10 to the minus 9. So if I compare the two concentrations, the concentration of H3O plus is greater than OH minus, which means the solution is acidic, and coffee is acidic. So a lot of people have trouble drinking coffee. It upsets their stomach because you're adding more acid. So if the H3O plus concentration is equal to the OH minus concentration, the solution is neutral. If the H3O plus concentration is greater, it's acidic. If the H3O plus concentration is lower, it's basic. pH, you may have heard of this. It's a measure of acidity. There's a scale that goes from 1 to 14. The pH, it's a small p, capital H, is calculated by taking the negative log of the H3O plus concentration. This is why you needed a scientific calculator that has logs on it, so you can do these calculations. So if the pH is less than 7, it's an acidic solution. If it's equal to 7, it's a neutral solution. If it's greater than 7, it's a basic solution. Well, we're going to spend some time doing these. So if H3O plus is 1 times 10 to the minus fifth for a urine sample, what's its pH? So to do the pH, we take the negative log of 1 times 10 to the minus 5, which is negative 5, which is 5. So the urine sample is acidic because the pH is less than 7. So right now,